Hi everyone, this is Pradnashil again, and here we have Saurav. So yesterday was day one of workshop on zero knowledge. Okay, so today is the second day, and we will be working on project today. So yeah, I'm handing over this workshop to Saurabh now. So all the best, guys. Have a great fun. Yeah, bye.
Okay, welcome everyone. So, yesterday we were here. We did the proof generation part, but we left the solidity part to generate the solidity file, etc. So, let us do that today. But to save time, we won't be working with that multiplier example which we did earlier, but a slightly more intricate example, a slightly more intricate circuit. So, we will use that circuit and generate the solidity file, etc. for that circuit. So, the circuit, the concept which we will work on is basically we want to give the voting rights to only that person who is above the age of 18, either equals to 18 or greater than equal to 18. So that is what we want to have the constraint. In the solidity verifier, the age threshold will be set as 18, and the user need to prove that his or her age is greater than equal to 18 without revealing the actual age. So that is the logic which I want to code here. So moving to my editor. Okay, so this is where we were yesterday. So let me just delete all these files since this is too much of clutter. Okay, so we are fresh in this. Now we will be working with a plugin known as Hardhat Circom. So let me also show you its npm page. All right, here it is, its npm page where you can read more about this plugin. So let me follow all these instructions. Basically, first we will install this package, then in our hardhead configuration file, we will add this require statement to have it imported, and then these few settings is what we will do, which I will explain also. So let me jump to the terminal. All right, so I am in my that directory, that backend directory which we created yesterday. So let us first install that hardhat circom package. Yesterday, if you remember, that we also installed a package known as circomlib. So that will also we will use today. The idea behind taking this example was that I wanted to introduce to you like how do we use templates in our main template that we will be working with, how do we import some other templates in it, and like that. So okay, I have had it set up. So now let me also make suitable changes in the hardhat config file that we have here. So let us first do this require part and have this hardhat circum thing set. Then here let us make it 15, and I hope you know that here I'm just specifying the solidity version, like which version of the solidity I want to work with. So that is what I have specified here. Now the first setting that I'm going to put, which is optional. I mean, optional in the sense the directory which I'm assigning it to, which is circuits. This is by default, it will take this circuits directory itself for to find the circuits which I will specify next. So this was something, even if I would have not put this line, even then it will look up for the circuits defined in this circuits folder. Fine. Next, we will take this ptau file, and I told you that for the R1CS, the rank 1 constraint system part, we can abstract the phase 1. I mean, it is called as phase 1 ceremony. So, and then the contributions we do to the zkey file. So I hope you remember that. And regarding this ptau file, let me also show you a bit more here. Just a second. Okay, I am in this IDN3 SnarkJS page, and if you look at the ptau file, there is here they have given various ptau files. Now, depending on your constraints, you can take any of the files. So, I mean, the suitable file. So, for to the power 8, which is 256. So, in case you have less than equal to 256 constraints, you can take this file, and so on. I usually take this 32,000 constraint file just like that. But there are actually helper utilities which analyze your circuit, and depending upon the constraints, they automatically select the suitable ptau file. But let us not work with those tools here, but I will give you a pointers about where do the tools exist in the description or either in the comment of this video. So, and to select them, you can just right click and copy their address, or you can even download them there. But I usually work, I mean, let me check, let me not check that here. I already have some links of the ptau file which I use in general, so let me use them here also. So I'm just going to paste my link here, which I usually use. So for the to the power 15 constraints, I have this file, and this is something you must specify. I mean, this input based path you could have ignored, but this ptau file you must specify. Next, we have our circuits. Here, each circuit will be in its object. So you will specify your circuit name basically. And how do you specify the circuit name? So first of all, let us create the circuit. Say acheck.circom. So this will be my circuit. So in that hardhat configuration file, you specify the name. Okay, name of the file, right? So age check that dot circom thing is not required. There is even one more setting here to specify which protocol will you follow, the growth 16 or the plonk. So by default it is growth 16, so you need not specify. And there are other settings also available. The default ones are good enough for us. In case you want to explore those different settings, you can look at the npm page. Fine. So this is the age check circuit which we will work, and this is where our this part is complete. So that configuration part is now done. So let us now work with the circuit. Okay, and this is where I would also like to introduce various other like concepts regarding this circuit thing. So let's start. So the first line, we are specifying which circuit, I mean which compiler version we want, and in this case 2.0.5. Next, let us define a template, again the first letter being capital. And then in the end, I mean I will take this main component to be this circuit. So like this, you can do that. Now I want you to think what we want. The thing is, we have one signal, I mean one restriction, that the age which I mean first input signal will be the age, right, which will be the private, and that age has to be greater than equal to 18. Fine. So the prover wants to prove the age is greater than equal to 18 without revealing the actual age. So that is what we want to implement. I would like you to think, how do we do that? Fine. So let me also like start writing few things. So this is our private which the user will give. Next, we have this age limit. This will be public, set by the verifier. User can of course generate proofs with whatever age limit they want, but the verifier will set this signal since it will be public, so the verifier will set this to the 18, right? Next, we want to determine whether this age is greater than equal to age limit or not, right? Whether this age is greater than equal to age limit or not. So that is the thing. So let me make a signal. I'll declare it as output, and I'll also explain like why am I declaring it as output. But let us first, I mean, of course, this is not input. I mean, I want to apply a constraint to this thing somehow that age is greater than equal to age limit holds. And of course, I mean, this greater than equal to something is not a quadratic expression. We cannot use it to define our constraints. So it is slightly, I mean, when you think about it, it is somewhat complicated. Like, how can we implement greater than equal to something without using that greater than equal to symbol? But it's not that tough. I mean, it's as such easy. So, to explain that, right? I mean, you can of course think about it, but let me just quickly show you how they have implemented this greater than equal to logic. So in the node modules, we installed the circumlib, right? Yesterday. So circumlib, circuits, and this comparators. Fine. Yesterday we understood this is zero thing. So let us understand this less than template. Let us try to understand this less than. Basically, it will compare this input is an array of containing two elements. Suppose the first element is a, the second element is b. So this template's job is to determine whether a is less than b. Fine. If we understand this less than thing, then greater than thing, all these other things are using this less than only later. So understanding this less than is good enough for our purpose. So first of all, what is this n? This is taking as an input. This n is the number of bits. You will want this n to be the number of bits in your elements. So suppose my element is 6, right? My first element is 6 and my second element is 7. And I want to determine whether 6 is less than 7 or not. So 6 can be represented with 3 bits. Similarly, 7 can be represented with 3 bits. 7 binary representation is 111, and the 6 binary representation is just that, 110. The last bit is 0. 111 minus 1, right? So this n will denote the number of bits in your signal, right? Now here they're having this assert statement that n should be less than equal to 252. In case n is not less than equal to 252, in that case, this won't compile. This won't compile. And also, this assert has the implication in the witness generation case. I will explain that witness generation thing later. So, and why this 252, right? Why not 256? You might think. So, first of all, the prime number which we work with in Circom and also in pre-compiled contracts of Ethereum, the prime number which they are using is 254 bit, right? So that pre-compiled contracts of Solidity. So in case you will look, that prime is what they are also being used. Circom is also using here, and that prime is 254 bit long. So certainly, and we cannot work. Therefore, we cannot work with numbers larger than that prime, right? So larger than equal to that prime. So that whole 254 bit space is not available. So at most, I mean, but 253 bit space is available, and the entire 253 bit space is available to us. Then why are they not putting less than equal to 253? Why are they putting less than equal to 252? That is something I will explain here. So let us just continue reading this template. Then this input is taking, as I told you, two inputs we have, and we have to determine whether in 0 is less than in 1 or not, right? To determine whether in of 0 is less than in of 1. So that is what we want to determine. And the component here, this template will use this less than template here, and the output of this less than template will be taken by this template. We will see how. So this output will store the result, whether, I mean, this will be 1 if this is true and 0 otherwise. Fine. Now here is the magic, what they are doing here, and this is something I'll take time to explain. So let's see first of all what they are doing. This num2 bits. So what this function does, this function simply takes the input and give the binary representation of that number, right? So in case suppose in 0 is 6, let us assume this in 0 is 6 and in 1 is 7, then these both can fit in 3-bit number. So therefore we will give this less than having n to be equals to 3, since they both can fit in 3-bit number. And now in this num2 bits thing, they are making, instead of passing 3, they are passing 4, right? As such, when we are calling this function independently, I mean, here due to some reasons they are taking 4, which I will explain, but as such the 3 was fine. If we would have called this function num2 bits, what num2 bits is taking the number of bits. So here if we would have passed just n, then we would have got those n bits, those 3 bits in our case, of that number, which is fine. But here they are taking plus 1. So the most significant bit will, I mean, they are giving one more bit here. But if suppose if I pass 6 to this n to b, here in the n to b dot in, they are passing some other value. They are not passing in 0 or in 1. They are passing some thing, some clever thing. But if I were to do suppose this n to b, this dot in, and you know, then what will happen, the most significant bit will be set to 0, because I have made 4 bits here, and therefore the, the most significant bit, I mean the fourth bit, will be 0, because the representation of 6 in case of 4 binary digits will be this, right? This is what 6 in, decimal is, right? And also this num2 bits is something which I explained yesterday also. So that it is in this btfile file, and you see they are including this btfile.circom file, which is defined here, and this is how they include it. If you want to include some other file, you simply give like this: include btfile.circom. I mean include whatever file. So here they have this num2 bits, and this is something which we also saw yesterday. So for using this shift operator, they are finding the, ith bit. So for the 0th bit, we are not actually then performing any shift, because shifting by 0 is that same number. And then they're taking and with that 1, right? So 1 is what? 1 is this. I mean, if I were to show you, wait a second. Okay. 1 is, 0 0 0 so on, and in the end we have 1, right? So when they're taking and with that, then only the last bit of this thing will be caught. So shifting by 0, the last bit, the very, the most least significant bit will be caused in the first iteration, and then they have assigned that bit. And similarly for the next iteration, they will shift that number to the right by 1, and then catch that bit here. So then we would have got the second bit, and so on. So this is something which we even saw yesterday. So let us not put our time here. This is that num2 bits which I showed you in the documentation yesterday. Okay. So, and that is what this less than is using, that same num2 bits. But to this num2 bits, they are passing as an input this value, and this value is the magic trick. So let me explain you this thing. So first of all, what if you look at it, what is this doing? In 0 plus to the power n minus n1. So in our case will be, this will be 6 plus to the power 3, right? N is 3, so 6 plus to the power 3 minus 7. That is what they are doing here. So let me explain that with the help of some doodling. So just let me open that software. Give me 1 second. Okay, so you saw that to that num2 bits n plus 1, the input which they are passing is this in 0 plus this. You can write this simply as to the power n minus in 1. So in our case this will be 6 plus to the power 3 minus 7, right? So okay, now what I want you to know, this 1 shifted by n, right? We are working with 3 bits number. Its binary representation is this, and its binary representation is this, whereas the binary representation of this is this 1000. So it is having all these 3 bits set as 0 and the n plus 1th bit set as 1. So here we are doing 6 plus this 8 minus 7, or yeah, this thing is better seen here. 6 plus, yeah, to the power 3 minus 7. Okay, now for the general case, this is this, right? And all these are n bit numbers. Then if I also also write the output logic which they have written there. So this, to this output they are assigning this. I mean, this is something you can also check in that circuit. I'm just writing that same value here. Yeah, they are taking the last bit. This out is a n plus 1 bit number. I mean, this is what that num2 bits we pass to that num2 bits n plus 1. So this out is a n plus 1 bit number, and therefore the array indices go from 0 to n plus 1 minus 1, which is equals to this n. So that is how we can access this nth element. And the logic is just that in case of 6 less than 7, then it is true, and therefore out should indeed be 1. Out should indeed be 1, so this thing should be 0, right? And in case we look here, this entity, then this expression, let me take some other ink. This expression, you can write it like this: to the power 3 minus 1, right? Because 6 minus 7 is minus 1. So to the power 3 minus 1, and therefore this to the power 3 was this number, right? So when we are doing minus 1 here, then this will become 0, and I mean this will become 0, and then we will have some value for the other bits, in this case this whole, right? So for the general case that I wrote here, in case a is less than b, if a is less than b, and since these all are n bit numbers, we will have this to the power n minus some n bit number, right? And if we, and in case a was say greater than b. In case a was greater than b, then we will have, and let us take the extreme case here. Let us make this a minus b the maximum possible value, so that maximum possible value will be when all the n bits of a is set as 1 and all the n bits of b is set as 0, right? That is the maximum possible value that we can get for the a minus b. All right. And when the all the bits of a is set as 1, you know, so if I also do that, if a is, let me just erase that here. If a is, this 1 1 1 whatever, this one, where this is a n bit number, and b is 0, right? So this a will be equals to the power 0 plus to the power 1 plus so on plus to the power n minus 1, which is equals to the power n minus 1. This is what the a will be. So what we will have is to the power n plus this thing, to the power n minus 1. And if you look at this, to the power n, let us work for n equals to 3. Then to the power n was this number, right? All these 3. And what is this to the power n minus 1? Having these last 3 bits as 1. So you saw that this will not overflow. This will not overflow, and the n plus 1 bit in these cases will indeed be 1. The ultimate result we will get is this, all 1 here, and the last bit here. So the last bit will be 1, and 1 minus 1 will become 0. 1 minus 1 will indeed become 0. So that logic which we wanted, that in case a is greater than equals to b, the last bit becomes 0. So that is how this less than, oh wait, I need to also shift to the Visual Studio Code, not this one. Okay, so I hope you were able to understand the working of this less than thing. So let me just undo all, everything which I wrote. I don't want to mess with these files. Yesterday we messed with this is0 file, so I wonder whether I did any I mean, yeah, I think it's in its original form here. Okay, so we will basically use that that this, like we will use this greater than equals to here, which is indeed using less than, so not a issue here. I hope you have understood the working. Let me see whether is there any comment or question. Oh, I see some hellos. Okay, nice to meet you all. Okay, so let's write the further code. And regarding this, there is something which I want to explain in this line also. Like, why are we declaring it as output? We could have declared it as intermediate signal and so on. Why? So I mean, about this I want to explain few more things, so we will see that later. So let me now use this greater equal than thing, but of course I will also need to include that. So let me just quickly do that. Okay, so we will work with 7-bit numbers, because let me just write that. To the power 7 is 128, right? To the power 5, 32, 64, 128. Yeah, so maximum age, I'm assuming, I mean, the wait, the way I should write this is, when we are working with 7-bit numbers, then the range is from 0 to the power 7 minus 1. So 0 to this 127. So I'm assuming the maximum age to be at most 127, right? I mean, and all this code that I have written, I will put this in the GitHub repository in a better form. I mean, I will make all these comments to be more verbose. So now the thing is, how do we, work with this component that we have created? First, we need to, specify the inputs. This component is taking two inputs. So that is put that. And only after we have assigned the inputs can we use the output. If we would have tried to use the outputs beforehand, then it would have given us a compile time error. That is not allowed. And in this component, there are this age limit will be the public signal, and of course output signals are by default public, so we need not specify them here because they are public by default. Only for the input signals inside the main component do we have to specify this public thing. And of course the intermediate templates like this, all its signal are private. Only for the main component, like we also have this greater than component here, right? But only for the main component do we have that output signals all are public, and for the input signals we can specify which of them we want to be as public. So let us review the code here. Right now, okay, we have this greater than component and greater than equal to, so it will determine whether this age is greater than equal to age limit, because that is how I've constrained this way. Right now, what I would like to tell you, okay, so here this value will get constrained to whatever this is producing. If this is producing say as 0, then is age above limit will be constrained to 0. And if this was putting it out as 1, then this will be constrained to that 1. Right? We want that this, I mean, for the proof is valid when this is 1, right? And for that case, like if you notice, this thing is a output signal and therefore it is public. So the verifier can say that this signal I am making as 1, since this is a public signal, and this age is of course, this age limit is also public. So the verifier can say that it is 1. So even if this was 1 and here we are having it constrained to 0, then the proof will be valid. Right? So this circuit is complete. What I'm trying to say here, that if you try to write something like this, then in my opinion this is not okay to do. Why? Even, what this is doing, the one thing which I want to also tell you, that when we are using this triple equal sign, when we are using this triple equal sign, then implies also the generation of assert in the witness generation file. Basically, when we are constraining this something to something, then an assert is also taken out in the witness generation file. Like if I show you the documentation, but before showing the documentation, the one thing which I want to say, since we are asserting it to be as 1, then it won't be possible to generate the invalid proofs, and I don't want that. I want the people to be able to generate invalid proofs, and the verifier then can tell whether your proof was right or wrong. Right? But if we are having this constraint and as 1, then 0 will not be, 0 can't be constrained as 1. Then when we are generating the proof, when the prover is trying to generate the proof, say invalid proof, then in that case, uh, using this witness generation file which we use, that will give out the error, so that we won't be able to generate the proof, and I don't want that. I want people to be able to generate the proof, and the verifier can then tell whether your proof was valid or not. So if I tell you about this assert thing, so let me just show you the documentation really quick. It will become more clear as we are having this whole application built. Then at that time it will become clear. So this code is session. This statement introduces condition. You saw that in one of that. I think in this only, this less than we were using. Introduces conditions to be checked at execution time. If the condition fails, the witness generation is interrupted and the error is reported. See, that is what I'm telling you, that the witness generation gets interrupted. And recall that when a constraint is introduced with this, so whenever we are using this triple equal, even when we are using that, this less than symbol and then that triple equal, or that, I mean, double equal, even then, that is equivalent to having those two statements where one is this triple equal and one is that single arrow. So even in that case, the assert is automatically added to the witness generation code. So when a constraint is introduced with this triple arrow and at the other symbol also, which I told you, then an assert is automatically added in the witness generation code. So that is why I have it here in that, if I show you the way it is. So I'll add more comments to it when in the GitHub, but our code is, complete here. That circuit part thing is done here. Now let us work with the, magic of that Hardhat Circom, which we installed. So I'll just move to the terminal here. Oh, wait. Just one thing before I, move to the terminal. That plugin is requires that I give the, this file, which I just put here. So I need to give these two inputs here, age and age limit here. This age, we can work with any age, suppose 18, right? And this age limit, let us make it as 18. Okay. And I mean, since we are checking greater than equal to, right? So that is why I've also put age here as 18. But in the front end, the user can put any age. So we will code that also. Then the user can put up any age there. So, okay. So let me now move to the terminal. Here, when you do this hard hat, I think this is the command. It will show the available commands to us. And we also have this Circom command added via that plugin. So let me use that npx hard hat Circom. Let's see whether everything is fine or not. So it is showing that it is unable to compile. So let me also, use this command to see where is the error. Calling unknown symbol. Yeah, I have inserted this h here, which was the error. So let's try now. Okay, so now it has, successfully compiled. And by the way, I just removed that H in that symbol, which you were not able to see because I did not switch my window. So now if I move, so there was that H here, which I, removed. Now let us see what all the files it has generated. So this is what I gave already. Then it has generated this R1CS file, that verification key, wasm file, that z key which contains, the both the proving key and the verifying key. And then it has also generated this, verifier contract. Fine. So let me let us not I mean, play with the verifier contract here. First let us do the, front end part, so that we can play that time. So if I show you the documentation here at the very last they have a simple file. First of all, they have these commands to, have this SnarkJS we have installed globally, so we need not install that here again. But this npm init we have. And okay, and they have given some code, but the way I will be doing things, we will use some part of their code, and the other part is what I will use my own. So let me do that now. Here, this is where we are, right? So so let me just create a folder named as frontend, and let us just move into that folder. Here I'm going to put a pre-written file so as to save time. So let me just put the, give me 1 second. Okay, so let me just put the file which I had already generated, but okay, we are here only. But before I do that, let me do this npm init thing and hit enter to all these things. Okay, now let me paste the file. And regarding this, okay, so what I want you to do, we want to copy the file which they have mentioned. They have mentioned that we need to, like if I show you in their documentation, here in their HTML code, they are using this script source as this snarkjs.min.js, and therefore they are telling you to copy this file snarkjs.min.js for inside your node modules wherever you are having it into your current directory. But my suggestion to you will be, actually, in case, see, there is not much documentation about this snarkjs.js file, right? So you will have to look into the code for the different functions that we are going to use. I personally had to look into the code, and instead of therefore working with the minified file, it is better to work with the normal JS file, that's snarkjs.js, because in the browser when you are inspecting your console, in case you see some errors for the minified file, it is like very tough to see the errors. But for the normal JS file, you can easily then determine where actually is the error, like the argument, suppose whether the first argument needs to be, like here, whether the first argument needs to be proof or public signals. So all this you can determine when looking at the code, and in the errors also, using the normal .js file is far more comfortable. So if I also show you, and also regarding this, when you have installed globally your snarkjs file, you might be confused with what is your global directory, like how do I copy this file. The first method could be to copy from the GitHub repository itself, and the second method, first of all, you can determine your root directory using this command npm root -g. So this will give you your root command, which is this. And in case I this, so snarkjs, and inside we have to go to the build folder. Yeah, so this, as you can see, it has these 4 files. So we will not work with this minified file, because that file, if I show you also, is, it looks like this. And in the Chrome, when you are inspecting, it will give you some column number, so very difficult to work with, but that normal file is, wait a second, what did I just do, and why is it showing this has binary string? Anyway, in case I open it using code, oh wait, what did I just do? Okay. Yeah, in the code I can very much see it clearly. Like if I also show you, give me 1 second. Like here we have this, all this file, and basically whatever which you were able to do via your terminal. Like if I show you in the terminal, if I write here snarkJS minus minus help, you can see these things, right? Like here we can calculate witness using snarkjs. Either you can use this expanded thing, or better use this small wc, so witness calculate, then you can give your circuit input files and it will generate this witness file. So what all functionalities which you are able to see here, that is also available in that .js file. So for instance, we will use this solidity, I mean this exporting the solidity call data using that. So in case you want to see where it is, so you can just do something like this. If I show you, you can just try searching, say, yeah. So here you can see that, like here, wait a second, here we have this growth 16 thing which has exports already call data, which we will use. So let me not complicate all this here. So I'm just closing this file, and when we are writing this front end thing, then it will become clear. So moving back to my terminal, I'm just going to copy that file, that snarkjs file. So you need not see that being getting copied. So fine. Now let me also open this front end file, this front end directory inside the Visual Studio Code. So I have copied it, and if I go there, okay. So this is the index.html file which we will work with, which I have pre-written it. So here, so let me just run the server here. So let us first see what it looks like, and then I will explain it. This is what it will look like. The user will generate their age, and then when I'm clicking on this create proof, it will give me the proof here, and it will also tell me whether that proof was valid or not. And when I have this proof, I'm going to take this proof into my deployed smart contract. So we will use remix to have a smart contract deployed. I will show that. So let me also deploy the smart contract first, and then maybe we can see all that things. So here in that directory which we had, this is the verifier file which it generated, right? So the first thing, since we will be working with version 0.8.14, I'll make it 0.8. I mean 0.8.15, so I'll make it that. And you might be wondering whether is this even safe or not. I mean we just changed this a very important line, that 0.6.11 to 0.8.15, and we know whenever this second number is getting incremented, breaking changes are being introduced. But from my experience, I have seen many people just making this one line change, and it is working fine. So I guess it's fine. And inside this verify proof, this is where it will take those two public inputs. So I'll not make the change here now, I'll make the change later when I'm showing you. So if I go back to the browser, I am in this remix, and we have this verifier contract which I wrote previously, and I'm going to delete it. Now I'm going to create this new file, verify.sol. Here I'm going to paste that contract. Fine. And we will need to deploy this verifier thing. Okay, so this is set, and now the front end you have seen. So let us understand the code behind it. So let me move back to the Visual Studio Code. Okay, so title, this thing is fine. Header you saw. Then enter your age. I'm having this input tag, which I'm using id as age. So later I can, grab its value. Then this button generate proof. Then, you have seen that proof thing, result thing, both having their IDs. So I can, catch their value. Then I'm having my script. Right. So we will see their use and all this. To this, I mean, to this bgen proof, we need to have this add event listener. So whenever one is clicking that button, on click, I will call this calculate proof function. So this is my async calculate proof function. So let me also check whether are there any comments in the video before I move. Okay, so user will enter the age and I'll get its value like this document.get element by id, this age thing which I passed here, and then I'm using dot value to get its value. Then this input thing, I am making that age to be 8 and this age limit is 18. Since we want greater than equal to 18, I will also have this specified in the smart contract itself, but here also I'm having it specified. Then we are using this full proof thing. Earlier we first had this, basically we first created this witness and then we use this proof thing. Like if I show you the diagram which I have, like this is the diagram, right? Earlier we used this witness and then we did this proof, but SnarkJS also provides the functionality where I can use this wasm, this input.json file, and directly get the proof things, these two things, right? uh, Internally it will of course do these internal steps, but I can just, for the convenience sake, I can use that full proof thing. If I also show you what the documentation says, like here you can see we have this proof and we also have the full proof method defined here. So that is what being used there. So if I go back to that directory, I mean to that thing, so here, so this will take this input object which I have defined here. Then it will take, this agecheck.wasm file and agecheck.zk file, which is not present inside my front end directory. So I'll just quickly, copy paste these two files which we have generated before. Using that Hardhat Circom, we generated all these files. So I'm just going to copy paste those files here. So you need not see that. I can just wait a second. Yeah, GitHub. So, here I am. I've also copied one more file here because I have copied this agecheck.wasm file, also this what it required, that zk file I've also copied. I've also copied the verification key because we will need that. And then I'm doing this console.log proof and public signals. I'm going to, in the smart contract we will have our own this public signal, so that is fine. But here when generating proof, okay, then we are using this, this export solidity call data, just like how we have in the terminal using the snarkjs thing, we also have it here. So await snarkjs.growth16.export solidity call data, the proof thing and the public signals is what we have passed. So let me also make it sound what it is. Okay, then I'm also logging this public signals, not required as such, but I'm doing it. Okay, then verification key we are fetching, fine, and this is JavaScript part, we need not bother. Then growth16 dot verify, we are calling that verify function here, passing in this verification key, these public signals, right? Here I'm not using that public signals, I have my own public signals, which is, what is this public signals? Actually this, when we are, as such, when we will log the call data, let me first log the call data also, then it will become clear. So before I do that, I'm just going to have it refreshed. So I'm going to click on this go live again, and now here I am. So when I put the age as 18, since 18 is greater than equal to 18, it is giving me the result as indeed true. And when you look at this call data, if you look at the last two things in the call data, like if I show you this here, in this verify proof method, the last two parameters are these input thing. And if you look at the last two parameters, it is like this is 1 and this is 12. What is 12 in the decimal? So this is a hexadecimal number. So if we convert it to decimal, so 1 into 16 plus 2, which is 18. So yeah, this number is indeed 18 and this number is 1. So from here we can see that this is the output signal thing and this is that age limit thing. So here I will hard code it so that nobody can cheat with me. So I want this output public signal to be 1 and I want this age limit to be 18. So this is what I want, and this is what I have hard coded in the smart contract also. So even if I you know copy this and paste here, first I'm going to deploy this. Now I'm going to paste this here. Even though I have pasted the last two values, which but here I'm overriding it. So let me now click on this verify proof. It is calling the function here, and indeed it has returned me the value as true. So the return value input is all this, and you can see the last two things which I have overridden. And for the return value, I am indeed getting it as true. And here, so let me close this one. Here, if I put as 17, then the proof should be, invalid. And you can see I'm getting false. Now here, if in that Circom thing, if I would have made the constraint that out equal 1, then I will not be able to generate the proof for the 17 case. It will tell me that an error is encountered when I will inspect the, browser's console. So let me just copy this. It's taking too much time to go there. So let me just try copy this and paste it in that solidity thing. And that solidity part should return, false, because this is an invalid proof. So let me paste that here. I've clicked this button and you can see that it is indeed return me false. So I hope with this, all these things were clear to you regarding this, how to use SnarkJS, how to make your decentralized application via SnarkJS. And one thing more, here we used remix, but as such, when you are working with the circuits, it is better that you do in your local environment, because this remix thing, it might happen that even for this very small circuit, the constraints here are like, I think even less than 10, I mean just few constraints, 3 4 constraints, I guess. So even for this small system, it might happen that this page might become dead. So it is better that you use that other things like Hardhat to do this. And we have done this example. Of course, regarding this, ceremonies, how you can do the ceremonies, I will give you some links, some articles which explains how the traditional practice has been to generate the to have these ceremonies done, like semaphore ceremonies, etc. So I will give that also. As such, growth 16 is a bit fast, I mean faster than Plonk, but for small circuits Plonk can be used, and in that case you will need not, I mean as such it's not required to do this ceremonies thing, this, I mean that phase 2 ceremonies not required to have contributions in that. So this is where this session is ending. We have seen, how to use this SnarkJS thing inside your decentralized application. Here we, had it overridden here itself to make it easy for us. But in practice, you can have some other contract which will indeed call this verify proof method of this contract. So that's, I guess, all what I wanted to say in this lecture. So, Pradnashil, are you there? So that's it from my side. I'll just try to contact Pradnashil so that the session can be, wait. I think I showed the private info.
Hello. Hi everyone. Thank you for joining. Thank you, Saurabh. Uh, yeah.
Yeah,
So I hope you guys have learned a lot of things. I think this project will be added to your portfolio. Uh, okay. So yeah, thank you, Saurabh, for conducting this beautiful workshop, and
my
thank you once
pleasure.
again, guys. Yeah. So enjoy the Sunday, and yeah, tomorrow is Monday, and start working on it again. Okay. Yeah, man, guys. Bye. Have a good time.